In this section, we are talking about exponential functions. Okay, exponential functions are exactly what they sound like. They are functions that involve exponents. Okay? So first thing we need to talk about here is just our essential understanding that you can represent repeated multiplication with a function in the form y equals a times b to the x, where b is a positive number other than 1. Okay, and by the way, they said repeated multiplication because that's what exponents do. If I have 5 to the third power, remember that means 5 times 5 times 5. Exponents give us repeated multiplication. So exponential form, okay, an exponential function is a function in general form y equals a times b to the x. Please notice that only the b is being raised to that exponent. Okay, only the b is being raised to that exponent. It's a times b to the x. There's a couple of stipulations on that. A cannot equal 0. If a equals 0, then the whole thing equals 0, right? That means y would equal 0. B has to be greater than 0, meaning b has to be positive. B has to be greater than 0. And then b cannot equal 1. All right, that's our stipulation on this. B cannot equal 1, a cannot equal 0, and b has to be positive. So, in the next exponential function, the base b is a constant, meaning it's just a number. The exponent x is the independent variable with a domain of all real numbers. So they're just saying that x is your variable, that's your input, and its domain, which we've talked about domain in the last unit, domain is going to be all real numbers. So you can pick anything for x, from negative infinity to positive infinity. Okay? So to see what happens with these, what does an exponential function look like? We're going to go ahead and dive into graphing one. So we want to graph y equals 2 to the x power. Okay? And now something to think about. If you have no idea how to graph something, there's no clue. They throw a function at you or an equation at you and say, graph this. What do you suppose would be the best strategy for graphing this? And I'm saying this because we have NISA this week, and you kind of need to know a strategy that would work. If you have no idea, you have no clue how to graph it, what do you suppose you could do? So if all else fails, your best strategy would be just to plug in values of x. Okay? And since we haven't talked about exponential functions yet, that's really all we're going to do here. We're just going to plug in values of x, see what happens. Okay? And we're going to plug in a bunch of values of x, much more than we actually need to graph this. So we're going to make a big T-chart. We're going to make a big T-chart, and we're going to list it from -5 to +5 for our x values. Okay, so going from -5 to +5. We now have to plug those values in to our equation. So for -5, we're plugging in y equals 2 to the -5th power. All right, now we just got done with a unit on exponents. So how would I evaluate 2 to the -5th power? So this really means 1 over 2 to the +5th power. Well, what is 2 to the 5th power? I don't suppose anybody happens to have their roots chart handy, huh?
I do.
Well, I've got one here if we don't. That's all right. But you might want to dig it out for your homework. Okay? So on my roots chart here, if I look up 2 to the 5th power, I see that it's 32. So that means 2 to the -5th power is 1/32. Okay? 1/32. 1 over 32. Well, how about 2 to the -4th power? Well, what am I going to do with that? It's going to be 1 over 2 to the +4th power. All right, and 2 to the 4th power is Anybody know? 16. So when x is -4, y is 1/16. So on and so forth. So please take 30 seconds, fill out this t-chart. Okay, going through these, if we plug in -3, we're going to have y equals 2 to the -3rd power, which is 1 over 2 to the +3rd power, or 1/8. If I plug in -2, I'm going to get 1/4. If I plug in -1, I'm going to get 1/2. If I plug in 0, what is 2 to the 0 power? 2 to the 0 power equals 1. That was one of our properties of exponents. Anything to the 0 power equals 1. 2 to the 1st power. 2. 2 squared. 2 cubed. 2 to the 4th. 2 to the 5th. All right, so there's our extended t-chart. Lots of points to graph. But now we're actually not going to be able to graph all of these. Okay, we're not going to be able to graph all of these. Let's start with the big numbers. Let's start with 5, 32. Well, my y value, or my y-axis on this graph only goes up to 10. So I can't graph that one. It's off my graph, right? Same with the next one, 4/16. It's off my graph. But 4/8 I can do, right? Or 3/8, excuse me, yep. So 3/8 is there. Let's see, 2/4 there. 1/2 and 0/1. -1 1/2. Okay, now these are going to start getting really, really small. So I'm going to zoom in just to kind of show the effect here, okay? I realize you guys aren't able to do this as well. All right, so we were at -2 1/2, so now we're going to be at, no, I started with -1 1/2. Now we're at -2 1/4. -3 1/8. -4 1/16. -5 1/32. I mean, it gets ridiculous at some point here. Okay? But you can see in the graph that our points are getting closer and closer and closer to that x-axis, right? But they're never actually going to touch it. Okay, we went down to 1/32. If I go down to -6 as my x-coordinate, -6 is my x-coordinate, my y-coordinate is going to be 1/64. Okay, then if I go to -7, I'm going to get 1 over 128. Okay, keep taking half of that distance. It's going down by a factor of 2 because 2 is the base of the exponent. All right, so you're going to keep cutting that distance in half, and keep cutting that distance in half, and keep cutting that distance in half. So are we ever going to get to 0? No. We're going to get real, real close, but we're never actually going to get there. So this is what that graph looks like. It goes real steep there at the end, and then it comes down and it just gets closer and closer and closer and closer to that x-axis, but it never actually touches it. I know we draw it as if it's on the x-axis, but it never actually gets there. Okay? That's called an asymptote. That is called an asymptote. If I go down here a little bit, right there is what I'm talking about. An asymptote. Our exponential functions that we're going to be graphing today are asymptotic. Asymptotic is a fancy way of saying they have asymptotes. Okay? An asymptote is a line that a graph approaches as x or y increases in absolute value. Okay? So it's going to be the line that our graph approaches, but it never actually touches. That's what an asymptote is. And so the line y equals 0, which by the way, the line y equals 0 is the x-axis. Okay? That is the asymptote for the function we just drew. Y equals 0 is that value that our y values are approaching, but never going to actually get there. A couple of things to notice here. First off, notice that we were not able to actually graph all the points that we did. I mean, I do not expect you guys to graph probably these. I mean, 1/2, we can graph 1/2 pretty easy. 1/4, it starts to get difficult. 1/8 is getting ridiculous. 1/16, 1/36, those are all ridiculous. Okay, I had to zoom in to even get close to where they were supposed to be, right? So I wouldn't have you graph anything smaller than 1/2. Furthermore, obviously we can't graph anything that's not on the graph. Okay? So, I'm not telling you right now that you always go from -1 to 3. That's not what I'm saying. I'm saying you only need to graph the points that you can actually graph fairly easily. You want a lot of points, you want as many points as you can get on your graph, but don't graph y values that are so small you need a magnifying glass to get close. And obviously we can't graph numbers that are off our graph. Okay? That range will change slightly. You've got to pay attention to what you're plugging in when you're doing your t-charts. Okay? So let's try another graph. This one, y equals 2, 3 to the x power. What is being raised to the x power? Just the 3. This is 2 times 3 to the x power. Okay? This is 2 times 3 to the x power. So, let's go ahead and make our t-chart. Okay, and I'm going to start at -1, and I'll go up to 3. We'll see what happens. Okay, so if I plug in -1, y equals 2 times 3 to the -1st power. What happens to that 3? What's 3 to the -1st power? It moves to the denominator, yeah. So that means we get 2 to the 3rd power. Or I'm sorry, I said that way wrong. 2 over 3. We get the fraction 2/3. Okay, we get the fraction 2/3. All right, well, the next one is y equals 2 times 3 to the 0 power. What is 3 to the 0 power? 1, so 2 times 1 is 2. Then we have y equals 2 times 3 to the 1st power. Well, 3 to the 1st power is 3. 2 times 3 is 6. Y equals 2 times 3 to the 2nd power. What's 3 to the 2nd power? 9. 9 times 2, 18. We might as well stop there because we can't graph that point. Right? That's way off our graph. So therefore, we're not going to be able to graph when x is 3 either, because that's going to be way off our graph. Okay? So I'm going to stop there and graph the points I can do. So starting at -1 for x, I go up 2/3 of the way. That's roughly there. All right, just ballpark it. Then 0, 2 is right about there. And 1, 6 is there. So we're only able to graph 3 points from our t-chart. Okay? But you've got to keep in mind what shape this function takes. If you look back to our first example, it's going to look something like this. It's going to have an asymptote of the x-axis. That means it's going to curve and then go along the x-axis but never actually touch it. Okay? And it's going to go steeply up to the right. So, graphing our function here, it's going to be real steep here. And it's going to curve, come down, it's just going to ride the x-axis. There we go. So these two graphs are examples of what's called exponential growth. Meaning, as x gets bigger, okay, as x moves in the positive direction, our y values get real large, real fast. The y values are growing. Okay? That's exponential growth. There's also exponential decay. All right? Exponential decay is just the other way around, where as the x values, and by the way, this red line is what's showing that red graph, as x is getting bigger, our y values are getting smaller and smaller and smaller and smaller. Now again, they're never going to reach 0 because that's the asymptote. Okay, but they're going to approach 0. They're going to keep getting smaller and smaller and smaller. That is exponential decay. Okay, and again, the x-axis here is our asymptote. So how do you tell the difference between exponential growth and exponential decay? Well, that is all summed up here in the concept summary. So please make sure you're looking at this when you're doing your homework today. For our function y equals a times b to the x power, if a is greater than 0 and b is greater than 1, then we have exponential growth. So now notice in the growth and the decay, a is always greater than 0. So we don't need to worry about that so much. The b is the important part. If the b value is bigger than 1, you're dealing with exponential growth. If the b value is between 0 and 1, that is then exponential decay. All right? So if the b value is greater than 1, we have exponential growth. If the b value is between 0 and 1, we have exponential decay. So that's why, if you look back at the original graphs we have, in that first one, the b value is 2. And so we had exponential growth, because 2 is bigger than 1. In the second one, the b value was 3. And again, 3 is bigger than 1, so we had exponential growth. The other piece of information given to us by that equation is our y-intercept. Our y-intercept is always going to be located at 0, a. Okay? So the a value, whatever that a value is in the equation, gives us the y-intercept. And again, if we look back at the two graphs we made, the a value here, well, there is no a. b is 2, so a must be 1. It must be 1 times 2 to the x power, right? And look here, sure enough, our y-intercept was 1. If you look at the second graph, our a value is easier to see here. The a value is now at 2. And sure enough, our y-intercept was at 0, 2. So by looking at the equations, you can see whether or not you have exponential growth or whether or not you have exponential decay. So that'll help you determine which type of graph are you going to be graphing, one that goes this way for exponential growth or one that goes this way for exponential decay. And you'll be able to locate that y-intercept because the a value gives you the y-intercept. So let's practice that real quick. Looking at our two examples off to the side. Example A. Is this equation exponential growth or decay? What do you think? This is decay because the b value is less than 1. So this is decay. And where's the y-intercept? So what's the coordinate of the y-intercept? Always give me as the coordinate. 0, 12, because the a value gives you the y-intercept. The a value is 12, so the y-intercept is at 0, 12. Okay? Let's look at part B. Part B. The b value is what? The b value is 2, so therefore that is going to be growth. And our y-intercept is located where? 0, 0.25, or you could change that as a fraction as 1/4. But if you left it as 0.25, that's fine. They mean the same thing. Okay?